The purpose of this lecture is to understand a problem in the linear regression model called the simultaneous equation bias. So in order to do that, we'll start out by looking at simultaneous equations. So let's get started with the definition of simultaneous equations. So let's say that you have actually two dependent variables. We can call them y1 and y2. And let's say that each one of them can be modeled using a linear regression model. In that case, we say that we have a simultaneous equations. For a concrete example, let's say that I'm trying to figure out the demand for gasoline and the demand for oil. And I assume that each of the variables can be explained by a linear regression model. So in general, when we have simultaneous equations, it's perfectly allowed and perfectly valid to allow, for example, y1 to depend on y2. For example, if y1 is the demand for gasoline, or actually, let's say that y1 is the demand for oil and y2 is the demand for gasoline, then it's pretty clear that the demand for oil will depend on the demand for gasoline. We use oil to make gasoline, so if the demand for gasoline increases, so will the demand for oil. But each regression model, for example, the regression model for y1, may also contain other explanatory variables, and the same goes for the second regression model. Both models may have explanatory variables in common, but you can also have explanatory variables that only affect one of the equations but not the other one. So here is a simple example of a simultaneous equation system. So let's say that we have two dependent variables. We will call the first one y1, and observation I for the first dependent variable will be denoted by yi, 1. And let's say that yi, 1 depends on yi, 2, the value of the second dependent variable, and it also depends on two explanatory variables, x2 and x3. The error term is denoted by epsilon I, 1, referring then to the first equation. Similarly, in this example, yi, 2 depends on yi, 1, and also on two explanatory variables, x2 and x4. So in this example, both equations have x2 in common, while x3 only explains y1 and x4 only explains y2. And the error term of the second equation is denoted by epsilon I, 2. As a concrete example, this could be the demand for two products. As a concrete example, let's say that we have data for several regions in a country, n regions. yi, 1 could be, for example, the average house price in region I, while yi, 2 could be the average price to buy an apartment, and yi, 1 depends on yi, 2, and vice versa, since a house and an apartment can be viewed as substitutes. We could have explanatory variables that affect both prices of house and apartments, and perhaps variables that are specific to houses and to apartments. These two equations are called structural equations, and they are simply meant to describe the structure of the model. Or another way to think about it, this is how we believe the data generating process looks like for each of the two dependent variables. So in the system, we have x variables and we have y variables, and we give them different names. So if it's the case that the expected value of the first error term, the error term of the first equation, conditionally on all the x variables, only the x variables, and the expected value of the second error term conditionally on all the x variables. If those expected values are both 0, then we say that the x variables are exogenous. The idea here is simply that they're determined outside the system. I do not have an equation or a data generating process for example, xi2. I don't have a structural equation that begins with xi2 is equal to something. So we simply think of them as being determined somehow, but we do not model how they are determined. On the contrary, we have one equation each for the y variables, so they are called endogenous variables. Endogenous meaning within, and they're determined within the system. As we will see in a second, it is not possible to claim that the expected value of the error term conditionally on the y variables as well to be 0. So endogenous variables are not exogenous. So another way of looking at simultaneous equations formulated as structural equations is as a system of equations which we can solve for the dependent variables. Remember, we have one equation for every dependent variable or one equation for every endogenous variable. So we will have exactly the same number of equations as we have endogenous variables, and typically we can solve such systems for the y variables. If we do that, then we get another system called the reduced form equations. As a concrete example, here are my structural equations. Think of them as the data generating process for each of the dependent variables. And in the DGP, it's perfectly okay to have y2 affecting y1 and to have y1 affecting y2. Now I can view this as a system of equations. I have two equations, and I think of my dependent variables as the unknowns, the variable for which I want to solve this system. So they are here, 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 and here. So what I want to do now is to solve this system of equations so that I get yi1 equal to something and yi2 equal to something, and in the solution there are no 2's in the first equation and there are no 1's in the second. Then I have what's called the reduced form equation. Structural and reduced form. So let's think about this process. How would you get the reduced forms equations? Well, there are many ways of solving systems of equations. One idea would be to start with the first equation, realize that there is a yi2 here. yi2 is exactly equal to this expression. So what I could do is I could just take this expression here and plug that in here, because that is yi2. Now once you have done that, you have no yi2 in the first equation. You have yi1 in two places, here and here, but you can just move this term over to the left and then solve for yi1. Once we have done that and we have a solution for yi1, then we just take that solution, plug it in here to get the solution for yi2. So that will give us these equations. Now there is one important aspect of carrying out this process, creating the reduced forms equations, and that is the following. The structural first equation depends only on the first error term. Similarly, The second structural equation depends only on the second error term. However, in general, the first reduced form equation will depend on both the first and the second error terms. So this one will contain I1 and it will contain I2. And the same goes for the second reduced one. There will be an epsilon I1 and there will be an epsilon I2 in there. You can see that from the process that we use to solve the equation. I do take this entire blob and kick it in here. Well, when I do that, I also bring this one. So that will now go into the first equation, and then when I solve that for yi1, it will stay there. yi2 in the reduced form will also depend on both error terms, because I will bring both of them when I plug in my solution for yi1 into the second structural equation. So a really important point and sort of the main purpose of this whole lecture is to realize that in a system of equations, the first dependent variable will not only be correlated with the first error term, but it will be correlated with the second error term as well. That will follow in general from the reduced form. The same goes for yi2. It's not only going to be correlated with epsilon I2, but with epsilon I1 as well. So there will be a sort of cross-contamination of these two errors into both of the equations. Alright, so since yi1 depends on both epsilon I1 and epsilon I2, and yi2 depends on both epsilon I1 and epsilon I2, it must be the case that when you look at the conditional expectation of the first error term given the second dependent variable, that expected value cannot in general be 0 because y2 is correlated with the first error term. Now it is by no means obvious, especially if you look at the structural equations, because from the structural equations the only thing we can see is that y1 is correlated with epsilon 1 and y2 is correlated with epsilon 2. But simply because y2 also depends on y1 and y1 depends on epsilon 1 will also affect y2. So why do we care about that? Well, the answer is, let's consider the first equation by itself. What we have concluded is that these two will then be correlated. The explanatory variables of the first equation, which are these ones, these are the explanatory variables, they are not exogenous, well, at least not all of them. So we know that if we run OLS on just this first equation, it is not going to give us unbiased and consistent results. The same will obviously be true for the second equation. If I try to estimate just the second equation, again, OLS will give you biased and inconsistent results. In this case, the culprit is here. That is not going to be an exogenous explanatory variable. So to summarize, y2 is not exogenous in the first equation and y1 is not exogenous in the second equation. Endogenous variables that appear as explanatory variables in another equation cannot be exogenous in those equations. So here's the main point then of this lecture. The structural equations in a simultaneous equation system cannot in general be estimated individually with OLS. If you have a system of equations, you cannot just simply pull out one of them and estimate that one using OLS. This is such a common issue that it has been given a name. This bias introduced from this simultaneous equations is called the simultaneous equation bias. Estimating a single equation that's part of a system will introduce this simultaneous equation bias. So the final point here is that, okay, well, I understand, but this is for systems of equations, and typically we only consider a single equation. But keep in mind that that is an assumption that may very well be violated. For example, let's say that yi is the consumption of a country I, and we model that as beta 1 plus beta 2 xi2, which perhaps is the GDP, plus beta 3 times some other explanatory variable, and so on. Well, even if you write it down as a single equation, that assumption might be invalid. In this case, you could just as well argue that GDP is partly determined by consumption, simply based on the GDP identity. Consumption is a big part of GDP. So it's really unclear here if the effect goes this way, or if it goes that way, or if it goes both ways. Whenever you have a situation where it's unclear in which the direction goes, you have what's called a simultaneity problem. And in such a situation, it might be better to set up two equations, one where y depends on x2 and one where x2 depends on y, where we simply promote the x2 variables from an explanatory to a dependent variable. If I ignore this issue and just estimate this with OLS, I am very likely going to subject myself to the simultaneous equation bias. But of course, the simultaneous equation bias doesn't always appear in a regression model. If I have another model, yi, which is, let's say, the result on a final exam, and I explain that with b2 xi2, where xi2 is the number of hours that the student studied on the exam, and maybe some other variables. And I ask myself, is there a simultaneity problem here between the result on the final exam and the number of hours studied? The answer is definitely no. You can argue that hours spent studying affects the final result, but you cannot argue that the final result affects the number of hours that you study, because one happens before the other in time. And as such, there is no simultaneity problem. So just to review, that's the final point. Whenever you consider a single linear regression model, if you can argue that not only does a particular x variable partly explain y, but you can reasonably well argue the opposite, that the x variable is partly explained by y, then you have a simultaneity problem, and you really ought to model this as a system of simultaneous equations.